focus on me. I'm going to spotlight everyone, remove all pinned videos. Joel Gray, everyone. Yes, continue. Okay. So I now have to go to share my screen. Right. I'm going to switch it over to student view because it's always a little bit different. That's not what I expected it to look like. Oh, goodness. What am I looking at? Okay, back. I'm not going to do student view. Sorry. We'll do instructor view. Hi, everyone. I'm Dr. Gray. I will be your instructor for CHEM 4375, which is a biochemistry course. This is a introductory survey biochemistry course. Many of y'all who are taking this are more than likely biology majors in some form or fashion. There's always a handful of animal science or exercise sport science majors. Yes? This is not GO1, but I can tell you how to get to GO1. So what you want to do, take your time, don't forget everything. Just don't forget it. So exit this building, I'll put you on kind of like a little landing area where there's some trees. Take the stairs down to your left. On your right, there's you can go through a breezeway. On your right, there's left stairs go through that. So left, right, and then one. Left, right, left. Does that sound good? Good directions? Okay, good. Okay, is everyone else in the right spot? Okay, cool. So I'm Dr. Gray, I'll be your instructor for this class. Like I said, exercise sports science majors, sometimes animal science, lots of biology majors in here. A handful of y'all are biochemistry minors. This is the appropriate class for you. There's also CHEM 3375, which is a class that is not exclusively for biochemistry majors, but if you are a biochemistry major, you need to take CHEM 3375 and not 4375. So I hope everyone's in the right place. The only thing that I've said that I think could get me in trouble, and I think that I've said this accurately, is that if you are a major, you should not be in this class. I've made some mistakes in the past of like, oh, don't go to this one. But also consult your academic advisor and whether that's in the college or in your home department. So in this class, we're going to go through kind of the foundations and the fundamentals of biological macromolecules. I'm going to use a handful of metabolic pathways for context. Some of these steps in these metabolic pathways, I do have the expectation that you know them. And I will make that what I think is clear that I do expect you to know them. And the reason for that is I personally think of a first semester biochemistry class as similar to if you ever took like a foreign language. It's like you learn how to conjugate the verbs, you learn how to, or you learn the names and whether it's masculine or feminine conjugations and everything like that. What are the appropriate words? But it's almost like you don't read a sentence. So it's like, in this context, here's how that word would end. It's like, oh, neat. Can I see that in a sentence? And the response is next semester. Well, that's sort of how this class is. And so it always feels to me, from my experience as both a student in this class and an instructor of this class, it feels like you're learning these things in a silo and you don't really get the connection between them. Or if that connection is there, it's very, very loosely threaded. So this semester, I'm going to be kind of explicitly and intentionally talking about metabolic pathways and bringing them up for that context and to establish that. So hopefully it will make a little bit more sense and it will be a little bit more coherent. Someone is in the chat. So we don't have a lab for this class. That's correct. Yes, that is correct. Was that someone in here texting, typing? And I'm not like you're in trouble, but instead I just wanted to make sure that that wasn't like a new function of Zoom where it's like if somebody's typing. Okay, okay, no worries, no worries. So that's kind of the overview of this class. Now, for how we're going to be kind of functioning in this classroom. We will be meeting physically here for this first week. The remainder of the semester will be a combination of, or a mixture of, synchronous and asynchronous meetings. So what I think that you should expect for a given week is Monday, there will be an exam. The exams will be administered on Canvas with the support of Proctorio. That's my plan and intention. In the event that I have a experience with Proctorio that just goes sideways, well, then I'm going to reevaluate that situation. I'm not going to be like, nope, I'm hell bent on this and this is what we're doing. Now, with that in mind, that gives a little bit of flexibility when you're going to take those exams. And the window that I want y'all to take those exams would be between 1 and 6 p.m. So the days that you have an exam would be between 1 and 6. So that's Mondays. Tuesdays are typically going to be asynchronous meetings. And so I will have everything that you need to do for that class day, your lecture, as well as any sort of top hat questions, homework sorts of things. Those will be available to you, and they will be open all day. Then on Wednesdays, we'll have a synchronous meeting where we'll go through, any questions that you had from the previous day, and well, anything new that occurs. Okay, next question. Sure thing. Then on Thursdays, some will be synchronous and some will be asynchronous. Fridays, most of those will be synchronous because what I want y'all to do is use Friday as the opportunity to ask any questions that you may have. Now, with that in mind, everything that we cover, you'll be given access to recordings of that. I'm going to post all the PowerPoints. As you can see here, I've posted my PowerPoint notes as a PowerPoint file. That's what PowerPoint notes is. Then PDF notes, it's the PowerPoint just converted to a PDF. I've learned that there's a generational divide between my students because I like the PowerPoint because then if there's an animation, I can see the sequence of things. But many people who use a tablet or something like that, the PowerPoints go completely sideways. So the PDF is there for you to use that, mark that on PowerPoint. Then I've also got the syllabus on here. Now, does anyone have any questions about basically the arc of a week? So Monday will be exam, Tuesday will be asynchronous, Wednesday, Thursday, and Friday, or Wednesday will mostly be synchronous, Thursday asynchronous, Fridays will be typically synchronous as well. And I will let you know, like, here's the projection for the week. Does that sound good? Okay, cool. In addition to that, I want to make myself available to you, and I'm going to have office hours. One thing that I've done in the past that I feel like it's hit or miss. Like one semester, I'm like, aha, I know what to do. I'm going to open the door for, hey, whenever you need office hours, shoot me an email, and then we can schedule a time. And I think that kind of works, but it also kind of doesn't work. And then I've tried the opposite end of the spectrum of my office hours are at this exact time. And that is whenever my office hours are. And there's typically someone who's like, oh, I can't do that because I work, or, I'm commuting, I've got class, or I've got another class during that time. What I think I'm going to do this semester is have designated office hours on Mondays, Wednesdays, and Fridays. And I will post those on our Canvas page as an announcement. I typically like to use announcements for Canvas. It's pretty rare for me to email you directly. If you email me, I'll respond to that, but typically things are going to come as announcements. And I want you to know that just because I know that if you're taking 2 classes or something like that, you might get a Canvas notification for the day is blah. And that will be like review all the things that you posted. Some people use Canvas announcements as like very, I don't know. They might you might be like, oh, I get so many announcements or so many notifications from Canvas, I don't need to read any of them. I want to say now that if you get announcements or any notifications from my class, it's important that you do read them. And I know everyone probably says the exact same thing. But that's my primary means of communication. Does that make sense? Okay, cool. So then I'll pull up the PowerPoint, because one of the other things that I want to talk to y'all about is grading. How you'll be evaluated in this class, where your grade's going to come from, and what you need to do basically in order to excel in this class and get the most out of this time together. Okay. CHEM 4375 hybrid. There we go. There's our overall rundown. Yeah, so sorry. Last thing is that the recording for today, I've recorded it to the cloud. So what I'll get notified by is, hey, here's your link. That link will remain active for 7 days. What I always do is I download those and I post them on my YouTube channel, because I want to be able to become a retired YouTuber. And y'all attending or watching that for, getting me upwards of 35 views per video, I think I'm going somewhere. So I'll download those links, or I'll download those and then I'll post those on YouTube. So I will send to y'all the YouTube link as opposed to the Zoom recording link, just because that expires after 7 days. But anyway, you need to watch the whole thing, because you need retained viewers in order to become a retired YouTube millionaire. I might be late to the game, but we'll see. Okay, so there's that. I'm being facetious. I don't think that I'm going to become a retired YouTube millionaire. I'd like to become a retired, I'll say, billionaire. And if there's YouTube celebrity that goes alongside it, I think it's probably just going to be a coincidence more than anything else. Intended for non-biochemistry majors. Then fundamentals of our molecules of sugars, fats, and amino acids. We'll use some metabolic pathways for context. Now, grading. We'll have quizzes. Those will be similar to your exams on Proctorio. I'm going to do the quizzes probably on Fridays, just so that you have that. And I'll have the quizzes on Canvas, and you're going to be able to give responses or get feedback on what your answers are, whether it's correct or not. Then we're also going to have Top Hat. Now, Top Hat can be used in a couple of different fashions. It can be used as, hey, during class, I have a question. Does everyone understand that? Yes, they do. We can proceed. But Top Hat can also function kind of as a homework platform. So I can have a series of questions that are open from 12 noon until 10 p.m. That's the way that I'm primarily going to be using it, just to accommodate for those instances when we have an asynchronous meeting. Does that make sense? So the Top Hat questions, I would recommend, watching the lecture or being in the lecture and then answering those, because they will be kind of summary sorts of questions from, hey, what you did today in class was blah. You do not have them assigned for today. And I would expect basically a 1 day lag on those Top Hat questions. So the questions over today's content will be available tomorrow at noon, and they'll close at probably 10 p.m. tomorrow night. So it gives you a 10-hour window to finish them. Does that make sense? Okay, and then Wednesday's questions will be available on Thursday, Thursdays on, and so on. Good? Okay, cool. So those two things account for 20% of your grade. If you look at my rate my professor evaluations, which I've looked at those, and some of them are fairly scalding. Some of them have said, like, he doesn't do homework. Everything comes from your exams. Well, this is both to kind of appease that person and to say, like, okay, I understand. That's a fair grievance. If people don't like that, I'm going to respond to people. The bulk of your grade is exams. Now, with that in mind, I want you to know a little bit about the exam grading scheme that I use. And this is, is this a touch? That is a touch screen. Perfect. So I'm going to draw on here. And yeah, there we go. So you'll have 4 exams. These are our Monday exams, and there will be a final exam, which is worth 20% of your grade. Now, exam number 1 will be exclusively over. I'm going to just refer to everything as week 1 content. Then exam 2 will be a combination of week 1 and week 2 content. So I'll try to make this as more clear. I'd also don't want to break this screen off. Week 1 plus week 2. Exam 3 will be week 2 plus week 3. 4 will be 3 and 4. And then your final is a cumulative exam. There we go, cumulative. Now, one thing that's absolutely important that you understand is that the final exam is 20% of your grade, regardless of how you do on exams 1 through 4. So if you roll into the final exam and you have perfect quiz points, perfect top hat, and perfect on exams 1 through 4, your semester average will be an 80%. And that's a B. If you elect at that point, all I wanted was a B, I'm not going to take the final, then that's your prerogative. If on the other hand, you, let's say, and the thing is, most people who are in that situation aren't the sorts of people who say, oh, all I wanted was a B. They're like, I'm a high achiever. Of course, I'm going to go and try to make a 100 on the exam. Let's think about this on a slightly different situation. And this is, I don't want this to sound like I'm judgmental or anything like that about this, but let's say week 1 or exam number 1. So on Monday, you missed that exam. What you're going to get for that exam, I'm going to have your grades over here on the left-hand side, would be a 0. Okay. It's the summer, it's a condensed semester, so it's very tricky to get things kind of aligned and positioned so that we can have lots of exams. So if you're in that position, I'm not going to do a makeup or anything like that. You get a 0. The reason or the thing about that is your exam 2 grade. Let's say that when that rolls around, you get a 95. Let's say you get a 95 in exam number 2. That is going to be your exam 2 grade. It's also going to be entered for exam number 1. So having missed that first exam, well, you are going to be evaluated on your knowledge of that content because exam 2 covers week 1 content as well. Now, let's say that on exam 3, you're riding high and you think, I know this stuff. I'm going to do great on this. Let's say that you get a 70 on exam number 3. Well, because my handwriting is funky, I'm going to call that a 76. You get a 76. There we go. And is that feasible? Yeah, that is. That's feasible because on exam 2, you did really well on your mastery of week 1 and week 2 content. And you carry that into exam number 3. If you had these grades, what would you be able to say about your knowledge of the different material that you've seen? Well, week 3 needs some improvement, more than likely. Does everyone follow that? So you have this kind of introspection and retrospective on your grades. You'd say, I think I'm pretty strong on week 2 based on my result on exam 2 and exam 3. Chances are I need to brush up on exam 3 content or week 3 content. So then let's say that you do that. You brush up on that week 3 content, exam 4 rolls around, and you get a 98. No, didn't really get any better. Okay, let's go with a pen. 98. You get a 98 on that. Well, that 98 is entered for exam number 4 and is subsequently entered for exam number 3. So what this means is here are your, sorry, chat. You can't see the, sorry about that, Zoom folks. Thank you very much for letting me know, Sam. Okay, so yeah, I'll just say that I hope that does not happen regularly. But sorry. So here's what I'm going to write out the way that it's going to be displayed in my grade book. And one of the downsides of Canvas is that the display that I see is different from the display that you see. So what I will see is I'm going to call this exam 1, E2, E3, E4. So for exam 1, you're going to have a 0 and a 95. For exam 2, you're going to have a 95 and a 76. We agreed that was. Exam 3, you're going to have a 76 and a 98. Exam 4, you're going to have a 98. And then the last thing that you're going to have is the final exam grade. So let's say that you come into class or you come in and you're ready to take the final exam, and those are the grades that you have. Question. For exam 2, because on exam, wait, just a second. Okay, so exam 2 is going to be, I'm happy that you asked that. The reason that you're going to have that is because your exam 3 grade can replace your exam 2 grade. So I'll get there and I hope that it will be more clear in just a second. You're also going to have a 3rd grade for exams 1, 2, and 3, and a 2nd grade for exam 4. That is going to be your final exam score. So let's say on the final exam, you get a 90. You get a 90 on the final exam. Now what I will see, and this is where it's going to be a little bit different from what you have and what I have. For exam number 1, under that kind of umbrella, that 15% of your grade will have a 0, a 95, and a 90. Okay. For exam 2, you'll have the score that you got on exam number 2. And then the next place where you're asked about exam 2 content or week 2 content, that was on exam number 3. So you'll have exam 3's grade. You'll also have, I'm going to write it down here for a little bit more clarity. Exam 3, you're going to have the exam 3 grade, the 76, the exam 4 grade, the 98, and the final, which is a 90. And then exam 4, you're going to have a 98 and a 90. Oh. Okay, now, does everyone follow me as to the grades that you should expect to have? Okay, now with that in mind, I'm going to, and this is something that, again, I can see from my end, but I want you to trust that it is a part of the calculation, is that for each of these categories, each of these weighted categories, I'm going to assign a rule. And that rule for exam 1 is to drop the 2 lowest. So I will, from exam 1, I will drop the 0 because you missed that exam. I will also drop, or not I, but Canvas will also drop the 90 because that is lower than the 95. So it's effectively going to say, when you were asked about this content, when was the time that you did the best? Well, exam 1, that week 1, you showed that you knew that week 1 material best on exam number 2. Okay, so that means the 0 and the 90 are scratched out. Now, if we go to exam number 2, you have a 95, a 76, and a 90. Well, the 76. So when you were asked about week 2 content on exam number 3, that's where this comes from. That gets dropped because that's your lowest. The 90 will also get dropped. Then for exam number 3, you have the score that you got the first time that you saw that on exam 2, the 76. Then the score that you got the second time that you saw that content, and then also the third time that you saw that content. What did you get? The third time being on the final exam. So the 98 is going to be the one that goes through. The exam number 4, well, you were asked about content from weeks 3 and weeks 4. And you got a 98 on that. And you were asked about that same content again on your cumulative final exam. You got a 90 on it. That 90 is going to be dropped. So what I want to be clear is I'm looking at when did you perform best on a certain set of material? Was it on your first exam? Maybe. Was it on your second exam? Maybe. If we look at this, if you look at these specific grades, the week 1 content, you showed that you knew that best when you took exam number 2. The week 2 content, you showed that you knew that the best when you took exam number 2. The week 3 content, well, you actually showed that you knew that the best when you took exam number 4. So effectively, the way that this person's or these specific grades shake out are going to be, and this is where it gets a little bit complicated, so bear with me and I'll bear with you if you have any questions, follow-up questions on this. Although here are weights, these 15s and 20 percentages, this person's grade, well, exam 2 is actually 30% of their grade. Exam 4 is also going to be 40 or 30% of their grade. Because exam 4, they got a 98, and that's going to move through as 15% of their grade for exam 4. That 98 is also the highest of the exam 3 grades, and that is also going to go through. That's why it's 15%. So where I'm going with this, or where I'd like to go with this, is the way that this is that your final exam will be worth at very least 20% of your grade. It's possible that there's someone who's like, you know what? I'm going to skip exams 1 through 4. I'm going to do that, and I'm just going to see how it works out. And I have no qualms with that. You make decisions in life, and this is where I say that, and that sounds very judgmental and like patronizing. But if somebody skipped exams 1 through 4, all of those grades could be replaced by their performance on the final exam. So what would the weight of their final exam be in calculating their grade? It'd be 80% of your grade. So your final exam will be at very least 20, and at very most 80. So where I'm going with this is it's possible someone says, you know what? I'm not going to do any of the quizzes at the top hat. I'm not going to do any of the exams. I'm still going to ace this final. That's great. I have no qualms with that. Like I said, that person, despite that tremendous display, will end up with a B. And that B will be as B of a B as B can possibly be. It will be an 80.0 if they get a perfect score on that final exam. Their chances, by skipping the quizzes, top hat, and all the other exams, what are their chances of making an A? 0. What are their chances of making a B? Well, their chances of making a B are just as good as their chances of getting a perfect score on that final exam. So where I want you to think about this is just to be like, okay, this is kind of my, this is, I guess, kind of a movement against the, hey, your final exam can replace one of your, or replaces your lowest. That to me doesn't make a lot of sense, because if your final exam is an even distribution of all of this content, if your final exam is 25% week 1 material, 25% week 2, and so on, maybe you just don't get the week 4 content. Well, does that really replace your knowledge of exam or week 2's content? It doesn't. So my effort here is to make something that's a little bit more of a reconciliation of, basically, you struggled with this. Well, let's see how you can do to improve that. So week to week, see if you can improve upon those grades. Does that make sense? To me, this is very, it's to everyone's advantage, because I'll give you your exams back, and well, you'll look at the questions, and or you'll have the opportunity to look at those questions and say, okay, well, this is what I didn't understand, or this is, oh, it was +4, I thought it was +5. Why was it +4 and not +5? And so those are things that I want you to bring to my attention and ask me. Okay, is everyone clear on that? Now, is this a little bit more complicated than most grading schemes? I think so. Is it unnecessarily complicated? Maybe. But I feel like this is the best thing for y'all as students. And to be completely honest with you, it's a kind of an easy thing to do with respect to writing exams. So I hope that if you have any questions about this and want any clarification on this, you will not hesitate to ask, especially, you know, as the final exam is getting closer. There is no doubt that someone will say like, oh man, I really want to ask about grading, but I feel like if I ask, then I'll be exposed for not understanding the grading. And this is the time that I'm going to say, by all means, ask that question. And I think that it's helpful to put together like, hey, if I did this on this exam, this on this exam, this on this exam, what would happen? And we can line them up. Like I said, though, I'll employ the rules on my end of the grade book, and the difference between what shows on my grade book from what shows on your grade book is I will have nice columns where everything's sorted out, and it will have the 2 dropped grades highlighted in red and the grade that is not dropped, not highlighted in red. From my memory of your grade book, it will be, you'll have 3 scores. You'll have that 0, 95, and 90. The 0 and the 90 will be a slightly shaded gray, and the 95 will be a little bit less shaded gray. So it might be like, were they actually dropped? And that's the thing that I always get that question, hey, were these actually dropped? And I would say 9 times out of 10, the answer is yes. Yes, I did set that rule. And that's something I like to do at the beginning of the semester so I don't forget to do it. Does anyone have any questions about grading? Okay, by all means, when these questions come up, please don't hesitate to ask. Okay, question in the chat. The Zoom people can't see. Oh, do you curve exams? That's a great question. And this is where I say, no, I don't. What I do at the end of the semester, I don't curve individual exams. What I do at the end of the semester, and I'm going to go ahead and clear my drawings here. There's all ink on the slides. At the end of the semester, what I do is I just line up the grades highest to lowest. And by my definition, 89.5 is an A. And let's say hypothetically, after all my grades are entered, I see the following: 89.6. And these are different people. Here's a person, here's another person, here's another person. Then 89.4. Then 89. Let's change that to let's go with an 80. Say that this is a 88.1. If I see those grades, ranked from highest to lowest. 89.5, bless you, is where I basically land as, okay, anything above that is an A. But I'm gonna look at those students, the 89.6 and the 88.1, or 89.6, 89.4, and the 88.1. And the way that I look at it is I'm gonna separate these two groups. I'm gonna say, well, these two students performed very comparably together. This person performed at a lower level than those two students. And so what I'm going to do is I'm going to kind of look for what I term a natural break. And I'm going to say, all right, well, 89.4 and above, that is going to be my A. And, you know, I generally do not say what the highest or lowest grade is, in part just because it's, excuse my language, but it sucks. There's always going to be someone who has the highest B. There's always going to be someone who has the highest C. And this person who got that 88.1, they're going to be like, oh man, your lowest was at 89.4. I was pretty close. If I only did this better on this exam and this exam, I would have gotten that. And I hate to like be so blunt, but my answer is yeah, like, yeah, I know. I'm sorry. And I'm not doing that with like a coldness and a like, oof, yeah, math. But this is where I like to split it up so that I can say, you know, because these two students, the 89.6 and the 89.4, you know, to me, that's like, I always like to think about an alternate universe. Well, those two grades are going to be flipped. Or if you give those two students the chance to take the exact same class all over again, same study habits, those two grades are just as likely. There's a level of like uncertainty and chaos that, you know, those two grades would flip. So they're so close together that I'm going to say that, yeah, that's where I land. The 88.1, that person consistently performed not, this is where it gets like, I'm not judging. I don't want to sound judgmental, but the person who got the 88.1, they performed lower consistently than the 89.4. Does that make sense? Okay, cool. All right, so long story short, I don't curve individual exams, but I will make minor tweaks and curves to the end of the semester. So your 89.4 might be an A. I'm not saying that it absolutely will, because it's pretty rare that someone gets an 89.40. It's usually like an 89.49. And I'm like, oh, that's a B. That's an A. Any other questions? Okay, cool. Well then, we will go ahead and get started with with our content for this semester. I am still recording this, which is good. That's good. So this class is a kind of continuation to some degree of an organic class. And there's a handful of things that you need to understand and appreciate about this class right from the beginning. You need to understand your intermolecular forces, strengths of different intermolecular forces, and kind of relative strengths of the intermolecular forces. In addition to that, you need to understand how functional groups fit into different intermolecular forces. Now, what we will encounter in this class is a limited number of these different functional groups. There are some that I need you to know just because it's going to be very helpful for understanding your amino acid structures. But before we get into that, one of the biggest differences between this class and your organic classes is we're working with everything in an aqueous environment. We're not talking about things in an organic environment. So it's pretty rare, if not, well, yeah, it's not just rare, but we will never talk about something, well, what's the solubility of this in hexane? Solubility of everything that we're talking about is in a water-based environment. So what that means and what's important for you to understand is there's a couple of things that are extremely important. One is pKa. Now, a pKa is something that a specific group has. It's a property that a group has that's intrinsic to itself. When you think about pKa, there's another two-letter phrase or two-letter term that should come to mind. What is that? pH. So pH is a descriptor of a solution. pKa is something that's intrinsic to a particular molecule. So there's a relationship between the pKa of something and the pH of a solution. So if something ionizes or does not. So that's one thing that I think is it takes a little bit longer for you to almost like recoil back to, okay, aqueous environments. This is a little bit more like Gen Chem 2 than it is organic with respect to how different molecules behave. Now, when it comes to your most important functional groups in biochemistry, they are your alcohols, thiols, your amides, and your carboxylic acid. Sorry, I lost it up there. So those four are going to be pretty much your most important ones and the ones that we see most often. If you think about an alcohol, one of the things that's important about an alcohol is that, well, can an alcohol participate, bless you, in hydrogen bonding? It absolutely can. Because when we have hydrogen bonding, what do we need for hydrogen bonding to occur? We need a hydrogen, right? What is another atom that we need? I'll give you a hint. There's three other good ones. I heard it very quietly. And I think I heard it both quietly and quickly. And I think what I heard was nitrogen acid fluorine. And that's cool if you want to say it so quickly and so quietly. But yes, you're absolutely right. For hydrogen bonding, we need a hydrogen, but then we need something like nitrogen, oxygen, or fluorine. Now, when we think about fluorine, over here in group 7 of the periodic table, well, more than likely, if that's pairing up with a hydrogen, well, it's going to make HF. Whereas oxygen and nitrogen, those two guys are a little bit more like, oh, well, they can participate in other sorts of bonding. But your alcohols are extremely important because they can participate in hydrogen bonding. So anytime we see a molecule, I think that it's important to ask yourself, well, can this participate in hydrogen bonding? Because what makes this class so much different from your organic classes is that, yes, a molecule can participate in hydrogen bonding, or our molecule that we're focusing on can participate in hydrogen bonding, but what else can? Our solvent. Our H2O can participate in hydrogen bonding. It's not hexane, it's not decane or anything like that. And I will say this now, and I will say it again over and over again. I am not an organic chemist. And that's not a judgmental thing. That's just the nature of what I studied in my life. So alcohols, thiols, carboxylic acids, and amides. Those are our four most important ones. We'll get into some other ones. We're actually going to get into some other ones today to see how they function and see how they work. But if you're going to say, I need to commit some of these to memory, start with those four. Now, with that in mind, it's important to think about, well, how can these groups change? How can they ionize? That's not the question that I'm asking today. That's just the thing that I want you to be kind of looking forward to. Okay, now this class is a biology class and it's a chemistry class, and the marketing people came up with a really clever name for it. That would be biochemistry. So we are concerned with a living system. Most often, whenever we talk about a molecule within a living system in this class, we're going to be talking about eukaryotes. So eukaryotes, or a eukaryotic cell or eukaryotic cell, would be something a little bit more similar to this rascal right here, because what's the fundamental part of a eukaryote that makes it different from a prokaryote? That's right, again, membrane-bound organelles. When we look at this rascal right here, Well, we've got a bunch of different components to it. We've got a nuclear membrane, a nucleus, nucleolus, chromatin, free ribosomes, endoplasmic reticulum, lysosome, cell membrane, mitochondrion, vacuole, Golgi apparatus, etc. Now, if you've taken a biology class, which I know that this class does not have a biology prerequisite, though, like I said at the beginning, many of y'all are biology majors, so you've definitely taken some. We don't go heavy-handed into like the cell cycle or cell division or anything like that. I just want you to be thinking about, well, we will talk about things that can happen in one part of a cell, but not in another part of a cell. And the reason that can take place is because we have these membrane-bound organelles. Because those different membrane-bound organelles can have different environments than, well, other membrane-bound organelles, or just the space outside of that membrane. Now, with that in mind, the part that's not really specifically designated is this kind of soupy solution where everything is. That's our cytosol. I will say cytosol as well as cytoplasm. That's our aqueous environment that everything's going to exist in. For this class, what we'll primarily talk about is, with respect to our membrane-bound organelles, we'll talk about the lysosome, because that's really a good trash compactor or a garbage disposal. Throw a bunch of stuff in there and it's destroyed. And then the other one, mitochondrion. What's the mitochondrion? Exactly, that's the muscle memory that everyone develops whenever they take a biology class. It's kind of like whenever I say, hey, what's the value for a mole? Everyone says, they just say it under their breath. And they're like, I didn't even intentionally do that, but it happened. So we'll focus on and talk about the lysosome, the mitochondria. And then from time to time, we'll talk about things taking place in the endoplasmic reticulum. So this is something that I don't want you to be like, I've got to commit all these different structures to my brain. Instead, think about, well, the lysosome, garbage disposal, mitochondria or mitochondrion is the powerhouse of the cell. It's where all your ATP is, or most of your ATP is generated. Now, how we study biochemical processes. We study them from the vantage point of thermodynamics. Thermodynamics is going to predict if a process is possible. We look at reactions just like you look at them in Gen Chem 2 as being spontaneous or non-spontaneous. We also look at them as being favorable or unfavorable. So when you see this, these three items here, I think that it's pretty fair to say that delta G is something that can kind of be coming back to your mind. Does anyone remember delta G, what that stands for? Gibbs free energy equation. Delta G equals delta H minus T delta S. Okay, so those are, again, Gen Chem 2, it was there. And I know that many of y'all, like myself, said, haha, I made it through Gen Chem 2. Now onto organic chemistry. Surely this is going to be the exact same thing as what I've done. Oh my gosh, it's not the same at all. Should I remember general chemistry too? I don't think I can if I try. That was my experience of going from Gen Chem 2 into organic. It was like a whole new world, but not in the fun, melodic Disney way. Instead, just in the, oh my gosh, it's a whole new, unbearable, scary world. When it comes to any sorts of calculations and equations, I will always bring those back up. But I just want you to appreciate that, yes, you've seen these things before and you did them once. So I want you to just kind of feel empowered and emboldened by, I can do it again. Deal? Okay. So we look at lots of reactions as being favorable or unfavorable and spontaneous or non-spontaneous. We also look at the kinetics of a reaction. How fast is a process going to occur? So when we talk about a chemical reaction occurring and the rate at which something's occurring, I think that it's helpful to put it in terms of like units. If, you know, whenever somebody thinks about speed, what do they think about? or speed and units. What's a unit for speed that comes to mind? Velocity, so like meters per second would be one, right? Okay, well, when we think about kinetics of a chemical reaction or the rate of a chemical reaction, do you think that we're still going to have that time interval? Something per second or per minute? I've got one vote no, and now I'm standing in silence. Does anyone think that the rate at which something occurs does relate to time? Absolutely. But if you think about an enzyme catalyzing a reaction, or a reaction taking place from like Gen Chem 2, for instance, were you thinking about how far this beaker is going to move across the table in 5 minutes? No, you weren't. You were instead looking at that as, okay, that beaker's not going anywhere. A reaction's taking place in there. I'm generating a product. So how can you measure the amount of a product in a chemical reaction? How do we measure a quantity in a chemical reaction or in chemistry? What are units for quantity? Give you a hint. It starts with an M. Molarity. Molarity. So molar or millimolar, nanomolar. So units for kinetic reactions in biochemistry would be something like nanomolar per second. So you're generating a product, nanomolar, that would be the concentration of that substance per second or per minute. Does everyone follow that? So when you think about kinetics, yeah, we are concerned with how long does it take to make that. And we want to know how much of that thing is made in that given amount of time. Does that make sense? So when we think about speed of a reaction, it's definitely a little bit different from like, how fast can I run? But there are some parallels and similarities. Okay, last but not least, equilibrium. Now, how far a reaction will go? How far is a reaction from equilibrium, and how much, how far is it from equilibrium, and is it favored to, well, it's obviously going to go back to equilibrium, but what do we have? Do we have lots of reactants or lots of our products? Now, when you think about equilibrium, what single letter comes to mind from the 26 letters in the English alphabet? I'll give you a hint, and you said it. K, absolutely. What's the other one that comes to mind that is non-equilibrium conditions? Q, absolutely. So Q would be your constant, or, well, here's your non-equilibrium conditions. We're primarily going to be focusing on K and the equilibrium constants related to that. Okay, so now let's go to our definitions. So equilibrium is a state in which forward and reverse reactions occur at the same rate. So you've got the reaction going forward, but it also is going backwards. The concentration of your reactants and products remain the same over time. So we have all chemical reactions proceed until they reach equilibrium. The equilibrium level for a reaction is intrinsic to that specific reaction. So if you have, like, I think that's one of the toughest parts about Gen Chem 2, recognizing that there is a balance between, okay, here's the amount of the product that's present, and here's the amount of reactant that's present. You have those K values that range from 0.00001 to a K value of like 10. Well, if you have K value of 10, what does that mean? That means you have more products at equilibrium than your reactants. If your K value is a very, very small number, much less than 1, what does that mean? That means you've got more reactants than products. So we do think about Le Chatelier's principle, or Le Chatelier's, if you're Ms. Olson, who was my French teacher in 7th and 8th grade, and in 9th, and then Miss Kostenbader in 10th grade. It would be Le Chatelier's, but they knew that I would come in and say Le Chatelier's. They'd be like, Joel, do you even try? I'd say, sometimes, je ne sais quoi. Any stress placed on an equilibrium system will cause that system to shift to minimize the effects of that stress. Stress can be placed on the system by adding or removing something from either side. Sometimes that is heat is added to a reaction. Sometimes a product is added to a reaction. An equilibrium constant or an equilibrium expression can be written for any reaction at constant temperature. So we have our lowercase a, b. KEQ is going to be your products at equilibrium, or the concentration of your products at equilibrium over your reactants at equilibrium. And so in the event that we have not evaluated by in the event that we don't actually have any experimental data so that we can classify something by its rate, we can look at an expression or equilibrium expression and say, well, the concentration of product C raised to the coefficient of C times the concentration of D raised to the coefficient lowercase d over A to A and B to the B. If you change the temperature of a reaction, you're going to change the equilibrium expression. Now, if KEQ, this is something that is very important to recall and to know, is that if KEQ is very smaller than 1, your reactants are going to predominate. I think that it's helpful whenever I give you a question that asks about a KEQ value and asks about reactants or products being favored, to just know this equation, products over reactants, and plug the numbers in, or plug in an arbitrary number. If your products are 1, reactants are 2, what does that mean? That means you're going to have a KEQ of 0.5. So you can just kind of use some deductive reasoning to solve that sort of question. Now, if KEQ is greater than 1, your products are going to predominate over your reactants. These are your equilibrium expressions. K is going to be a value, or K is that value that relates to, well, under non-equilibrium conditions. So that in Gen Chem 2, you had all these questions that were Q is this. Am I going towards equilibrium and making a bunch of products, or am I going towards equilibrium and making a bunch of reactants? Don't expect those sorts of questions, but instead expect questions related to what are the circumstances there, or what is the implication of a KEQ value of this or this. Deal? Okay. So yeah, approaches to the right. Okay. Now, to put this in the context of a biochemical system, we have a protein known as hemoglobin, which we will talk about when we talk about proteins and ligands and proteins and binding partners. We will refer to hemoglobin as HB. HB binds to 4 O2 molecules. So the binding partner of hemoglobin is O2. One hemoglobin protein binds 4 O2 molecules. So your reactants are HB, 4O2, and your products are HbO2 to the 4, or lowercase 4, subscript 4, because there's 4 O2 molecules that bind. This can be looked at as reactants and products. As a result, you can write an equilibrium expression for this. Boom, HbO2 subscript 4 over Hb, or the concentration of Hb times the concentration of O2 raised to the 4th power. Now in the lungs, and this is something we'll get into a little bit more, but in the lungs, there's an abundance of O2. The concentration of O2 is above the equilibrium concentration. So the O2 is picked up by hemoglobin, making more of that 4-oxygenated or tetraoxygenated hemoglobin, or oxygenated hemoglobin. The net result is the reaction is pushed to the right. So when there's a ton of O2, you push towards the formation of HbO2, or subscript 4. The KEQ does not change given that the environment is different. This is just a system that responds. It says, oh, well, there's a bunch of O2 in the lungs. Do you think it's going to have the same KEQ, or do you think that hemoglobin is going to have the same KEQ in the bloodstream? Yeah, the KEQ is going to be the same. But is the O2 concentration going to be the same? No, it's going to be lower. So the KEQ is not changed. The total concentration of hemoglobin, both bound and unbound, is the same. But in the lungs, we have a higher concentration of O2, so we have added more of one reactant perturbing that equilibrium. The reaction compensates by changing the concentrations of bound and unbound hemoglobin to get back to that equilibrium. So this is really kind of a primer for when we talk about proteins and ligands and how they interact, proteins and protein binding partners. I want you to look at this and say, okay, well, this is not so radically different from basically the second half plus of Gen Chem 2. It's equilibrium. It's asking about, okay, in the event that this concentration changes, what happens to my product? Does the product concentration go down or go up? Make sense? Okay. So, did I duplicate this slide? Oh, in the tissues, there's a lack of O2. The concentration is below the equilibrium concentration. So what's going to happen? O2 is given up by this oxygenated hemoglobin, and we're going to push the reaction to the left this way. The KEQ does not change because that's something that's intrinsic to that protein. And the total concentration of hemoglobin is the same, but in the tissues, there's a lower concentration of O2, so we have removed one reactant perturbing that equilibrium. The reaction compensates by changing the concentrations of the bound and unbound hemoglobin to get back to that equilibrium. Does that make sense? Okay, cool. Now, a biochemist's view of thermodynamics: life obeys the laws of thermodynamics. Living organisms require energy. Biochemists study the processes by which energy is extracted, channeled, and consumed by living organisms. The relationship between the structure and function of biomacromolecules is one way that we study thermodynamics. We also study it through metabolism. Thermodynamics of bioenergetics gives us a way to describe and characterize the energy changes in any biochemical reaction. Now, thermodynamics is concerned with only the initial and final states of the system or reactions or reaction components. It's not concerned with the mechanism or the process or how long it takes to perform that process. So it's the starting point and the end point. That's it. So your change in free energy, or your delta E, is equal to the energy of the final state minus the initial state. So when we talk about a chemical reaction, here's your free, like if you think back to a free energy diagram that looks a little bit like this. When we talk about thermodynamics, we're not so much concerned with this right here. We're concerned with that and that. Now we can dissect it a little bit more and get interested in that sort of transition state, but when it comes to energy changes or thermodynamics, we're concerned with that part right there. Now, the thermodynamic parameters of interest to biochemists are enthalpy, entropy, and free energy. Enthalpy represents the amount of heat absorbed or released by the reaction. Entropy represents the degree of order or randomness of the system. And delta G, the free energy, represents the amount of useful work that can be done by a chemical reaction. Now, I think that all of these things are components that you've definitely seen before. Go back to Gen Chem 1, I think it's the first time that you ever introduced enthalpy or entropy. Free energy comes in Gen Chem 2. I think that entropy is something that is always a little bit confusing because it's almost like speaking about double negatives. When the entropy when entropy increases, so delta S is positive, what does that mean for the disorder of a system? Well, if entropy increases, that means that system has become more disordered, correct? Okay. Now, I think that there's always like little folksy examples that you can think of. And I know that when entropy was first introduced, I think it was in one of my chemistry classes in high school, teacher was like, oh, well, there's always entropy. The universe is constantly expanding. And then your room gets messy. And it's like, it was kind of a jump that we just made, but I gotcha. And so I think that it's helpful to think about those examples, but really focus in on them. It's kind of like with oxidation or reduction. Everyone has a Leo the lion goes grr or oil rig. If you only remember oil rig and you go to the exam and the question asks you, is this species being oxidized or reduced? And the only thing you remember, I'm not like you cannot define those letters and you say oil rig. And I've seen this. People write oil rig on their exam and they think, well, crap, that's really where my knowledge falls off. Because after oil rig, I decided not to know anything about that. So when you hear that, oh, entropy increases, okay, that means my system became more disordered. So if you go from a pristine room to one there was a bunch of crap everywhere, the entropy value of that change is positive because the system, the room, became more disordered, okay? Then when you clean that room up, well, the system, the room became more ordered. So your entropy change is a negative value. So I just caution you whenever you think about these examples, okay, well, is that a positive or a negative change? To think about what the implications of that are. Okay, now thermodynamics. For chemists, we have a standard state. For biochemists, we have a standard state as well. And that just tells you that under standard conditions, if you think back to the thermodynamics of a standard state, or if you think about equilibrium for a standard state, does anyone remember what the concentration of your species are for measuring or when you talk about KEQ values? What did the concentration of your species have to be? Now, with that in mind, okay, when you're asked, when you get these sorts of questions where it's like, you've established a standard. You have these two reactants. Let's say you have two beakers of solutions. And you want to mix them together to figure out the equilibrium constant or the KEQ. Now, you're going to mix these two solutions together. Do you think that those two solutions would have a concentration of 125 millimolar each? Seems like kind of an arbitrary number. We're trying to establish like under standard conditions where you can do this in Ireland or someone else can do this in, I don't see anyone else with an identifying shirt or hat or anything that says another location. So you could, Mexico. We could do a chemical reaction in Mexico or in Ireland. I'm happy that we just went with countries and not defining actual cities where people actually live, but instead, in these two locations, these two broad locations, if I, from Ireland, report to you that, hey, I've done this reaction, KEQ is this, and you say, okay, well, I gotta try to figure that out. I gotta repeat what you did. If I say, well, the concentrations that I started with are the standards, you'd say, oh, okay, well, that's going to mean something to people throughout the world. Do you think that 125 millimolar would be just kind of an arbitrary number and therefore not a good standard to use? Okay, so that seems like kind of why 125, but that doesn't seem like a very good number. Okay, do you think that the concentration would be 0? Who thinks that they want to do a chemical reaction where they have a concentration of two solutions where both of them have a concentration of 0? Would any reaction take place if we mix two reactants? No, that wouldn't be good. What about a concentration of -1 molar? Exactly. Your quizzical look of, I've never heard of a -1 molar solution. So that's it. So we know that we have to have something in there when we're mixing our reactants to one another. What's like the simplest number that's not 0 and it's not -1? Yeah, it's kind of the loneliest number. So whenever it comes to a standard state, in Gen Chem 2, whenever we talk about a reaction under standard conditions, well, our concentrations of our solutions were 1 molar. So you'd have these two reactions, you'd mix them up. So whenever you say, well, I'm in Ireland and I did this reaction, I use standard conditions or I use standard state. My solutions had a concentration of 1 molar. My temperature was approximately 25 degrees Celsius. The atmospheric pressure was 1 atmosphere, or the pressure was 1 atmosphere. Now in Mexico, someone can say, aha, well, great, I'm going to do the exact same thing, the exact same temperature, pressure, and exact same concentrations. And lo and behold, what's going to happen to those two solutions, or those two KEQ values? They're going to be the same because they're done under the same standard conditions. Does everyone follow me there? Okay, so in order to compare those, we have to have a reference point or a standard state. Standard states apply to only one defined set of conditions: 1 molar reactants and products. Standard temperature of approximately 298 K. Okay, standard conditions are denoted by the superscript degree sign of a naught symbol. So that delta G naught and that delta H naught, that's under standard conditions. This was the enthalpy change of that reaction. This was the entropy change. This was the delta G. Is that familiar at all? Okay. Yeah, I think that one of your classmates did this. A little bit of a grimace, but yeah, familiar. Okay, so that delta G, that's a chemist standard state. Okay, now this is where I kind of draw a line between chemists and biochemists. And I say, well, they're different. Delta G is known as the standard free energy change. Does that phrase right there sound familiar? Okay, good. Now, biological standard states. Let's think about this. Standard states assume a concentration of 1 molar. So if you have a concentration of hydrogen ions of 1 molar, and you wanted to figure out, well, hydrogen ions, that's the same as what EM ion? A hydronium ion? H3O plus. If you had a solution, if I gave you a solution and I said, hey, this solution has a hydrogen ion concentration of 1 molar. It's acidic, absolutely. How did you figure that out? Yeah, negative log. You could take that 1 molar and punch in negative log 1 is equal to what? It's going to be 0. So your pH is going to be 0. Raise your hand if you have any cells within your person that have a pH of 0. No. So is it really appropriate, or does it make sense to study biological molecules in conditions where the pH is 0? No, it doesn't. Does everyone follow me there? So with that in mind, does a chemist's standard state work for a biochemist? No. If you said, think about it like this. If you were trying to study hemoglobin as an example and say, oh, okay, well, how much oxygen does hemoglobin bind? Well, I know that in order to figure this out, I've got to get an aqueous solution where I've got soluble hemoglobin, and that solution has to have a hydrogen ion concentration of 1. What do you think is going to happen to that hemoglobin at a pH and at a pH of 0? Now think about this. I have to be completely transparent and honest with y'all. On reddit.com from time to time, there will be someone who will post, if you're not familiar with Reddit or the internet in general, it's a really great place where people can go to feel better about themselves by insulting strangers. And there will always be someone who posts a picture of blood pHs. Your blood pH is probably about 7.4. Now, if your blood pH drops to 6.8, this person on Reddit will post a picture and be like, your blood pH drops to 6.8, you're dead. And then it's like, wow, that's really dramatic. And that person will be sitting at home being like, I feel really good about myself for making everyone else feel bad. And then I'll be like, that's why chemistry is important. That's what that person goes through that person's head while they're posting this. So we have a blood buffer system. Our pH of our blood and inside all of our cells has to be very well maintained at about 7.4. If it drops down to 0, what do you think happens to any of the proteins that are in a cell in our body if our pH drops to 0? We're dead. So a chemist's standard state does not work for a biochemist because we can't have conditions. It wouldn't make any sense to study environmental conditions where the pH is 0. Does that make sense? Okay. So there's that. But the pH in most cells is more than likely in a neutral or maybe even a slightly basic range. Biochemical reactions are buffered so that the hydrogen ion concentration does not vary. Therefore, we use a value of 1, not 1 molar, but a value of 1 for the hydrogen ion concentration. Now, additionally, in biochemical reactions, again, we're talking about something in an aqueous environment. The actual concentration of water in a biochemical reaction is approximately 55.5. Now, that's not a number that I want you to recall. That might be helpful for bar trivia or something like that. But I just want you to think about, we're in an aqueous environment. So there's more than enough water. So our hydrogen ion concentration, our hydroxide ion concentration, those are going to have a pretty significant impact on the pH of our system. But for the value, basically what this means is you can more or less, in many of these sorts of reactions, cancel out that H plus, because, or substitute it for 1, or substitute 1 for it. Therefore, we use a value of 1 for water. Now, since we modified the standard state to reflect these changes, or we have to make these changes, so what we're going to say is, chemists have the market cornered on delta G naught. But biochemists said, well, we like what you did there, but we want to add a little bit of flair. And that flair is with that apostrophe. And so that's how you know the difference between a reaction taking place under a biochemical standard state versus a chemist's standard state. Does that make sense? Okay. Now, biological standard states and cellular conditions. Standard states are useful for comparing reactions, just as they are in chemistry. But they apply to a specified arbitrary state. So this is, 1 mole of your products and your reactants. Cellular conditions rarely, if ever, match that standard state. Is anyone familiar with diabetes? I believe type 1 or type 2. One of the things that is common for people who are living with diabetes, they have to monitor their blood sugar level. And if I remember correctly, in the United States, we use all sorts of funky units, and this is not like, oh, we're so stupid, which is how lots of my teachers thought. I didn't really understand that. But instead, it's just kind of like, oh, well, you chose to go down the road less traveled. The rest of the world chose to go down this way. But I believe, if I remember correctly, units for measuring blood sugar in the United States is like decigram per centiliter or something like that. So you're measuring concentration of glucose in the bloodstream. So you have decigrams per centiliter. I could be wrong on this, a milliliter. Whereas most other parts of the world, they'll measure your blood sugar and it's going to be returned in millimolar. And so I think 5 millimolar is generally the concentration of blood sugar that is like a healthy range to be within. I want to bring that up because millimolar, we're not talking about something in a molar magnitude. We're talking about something that's 200 times smaller than that. And if you think about sugar or glucose as something that keeps your body moving and functioning, well, that fuel is kept at a very, very low concentration. So it's pretty uncommon to talk about any biological molecule in molar. Generally, we're going to talk about it in millimolar and nanomolar or something like that. So smaller units. So that's one of the other reasons why we do this. So we now use non-standard states for cellular conditions. Delta G naught versus delta G. Now, when we talk about enthalpy, for any processes, the energy of the system and its surroundings is constant. We can only convert energy from one type to another. We cannot make new energy. The internal energy of a system is equal to the heat absorbed by the system from the surroundings plus the work done on the system by the surroundings. E equals Q plus W work. Under constant temperature and pressure conditions, the total energy change of a biological system can be approximated by the heat evolved or absorbed by that system. Delta E is equal to our delta H. Now, enthalpy changes of reactions during a chemical reaction, old bonds are going to break and new bonds are going to form. This is just like what you learned in Gen Chem 1 and 2. Energy is either consumed or it's going to be released. If you have an exothermic reaction, you should expect a delta H value to be less than 0 or negative. So -1, -2, -250. Heat is going to be evolved by that system. New bonds are going to be more stable. In endothermic reaction, your delta H is greater than 0. Heat is absorbed by the system. New bonds are less stable. Nope, sorry. So a positive value for your endothermic reaction indicates, or for a delta H change is an endothermic reaction. Heat's absorbed by that system. Now, entropy. For any process, the entropy of a system and its surroundings always increases. It's a measure of disorder. An ordered state is always low entropy. A disordered state is high entropy. Delta S greater than or less than 0. When the final state is more ordered than the initial state, so a negative value, the products are more complex and more ordered. When delta S is positive or greater than 0, the final state is less ordered than the initial state. The products are less complex and more disordered. So if you think about this in terms of a compound, and we'll look at some examples where we see a couple of different molecules and how they react with one another to form a delta S that is going to be positive or negative, and kind of predicting that. Now, free energy, a change in free energy, or delta G, is used to determine the spontaneity of a reaction. Delta G is less than 0. It's an exergonic reaction. It's spontaneous and energy is released. When delta G is 0, your system is at equilibrium. When delta G is greater than 0, it's an endergonic reaction. It's non-spontaneous and energy is required in order for that reaction to be driven. So one of the most important parts about this slide right here is we will talk about a process known as energy coupling, where we have reactions that are basically coupled with one another. A favorable reaction, a spontaneous reaction that releases energy that drives a kind of companion reaction. Two reactions, like part 1 of a reaction is unfavorable, is favorable, and that is what drives part 2 to get us through this entire step. And if you think back to Gen Chem 1 and Gen Chem 2, you can think back to Hess's law as an example of where you looked at multiple steps in a process, where you had reaction 1, 2, and 3. Oh, reaction number 1 and 2, well, what do I have to do? If you remember Hess's law, that's where you would take a reaction and flip it in order to get it to match an overall reaction. So you'd have favorable reaction and unfavorable reaction. Okay, well, if I flip this, then this, then, okay, there we have my overall favorable reaction. Spontaneous and non-spontaneous reactions. Spontaneous takes place with no outside intervention. Reactions proceed from a state of high energy to low energy. An exergonic reaction, a non-spontaneous reaction, one that takes place without any outside intervention. Reactions proceed from low energy to high energy state. Endergonic reaction would be an example of that. Now, the amount of energy required to do work, well, what we have here is we've got this block moving up and this block moving down. So this would be a good example of coupled reactions where, well, this block in the blue space is going to go up, provided that this block in the red space goes down. If they were both in the blue space, neither would move. Only delta G is a measure of spontaneity. So keep that in mind, because it's easy to think about, oh, well, this reaction releases energy. Ah, fantastic. Therefore, it's spontaneously going to occur. It's not really how it works. And it's very tempting to say, oh, well, that is how it's going to be productive. That's how it's going to take place. But only delta G accounts for temperature, delta H, and delta S. Neither delta H nor delta S alone is sufficient to determine spontaneity, but they can be combined to give delta G. Delta G is equal to delta H minus T delta S. So our free energy change is going to be the combination of how much does our enthalpy change and how much order is involved. In addition to our temperature. So this figure right here shows which are our, you've probably seen something similar to this in past classes, where you looked at, okay, well, is this going to take place? Is this reaction going to give me a delta G that is positive? Is it going to give me a delta G that is negative? And so we have, if delta H and the product of negative T delta S are positive, what does that mean for our delta G value? That too is going to be positive. If delta H is negative and our negative T delta S is also negative, then we're going to have a delta G that is also negative. If we go all the way over to the right here, delta G, sorry, if our delta H is positive, but the magnitude of our negative T delta S is more negative, and that can be offset, then our delta G will be negative. So this last cell, with these last two on the far right, are going to be accounting for, well, under what temperatures? What temperature will get us to a delta G that is negative? So, because if you look at part C and part D, what do you notice about delta H in both circumstances? And sorry, just so everyone's clear, we've got this central axis, which indicates that we have a value of 0. Anything above this is going to be positive. Anything below is going to be negative. So if we look at C, what is delta H? Positive. Now, if we look at D, delta H, positive. Now, D, the delta H is slightly shorter. Is that significant? It absolutely is. Now, if we look at part C and our negative T delta S, that is going to be negative, just as negative T delta S. And part D is also going to be negative. So, dependent on either the magnitude of our temperature or the magnitude of our delta G value, we can have either a delta G that is positive or a delta G that is negative, depending on basically how far something is. So if a reaction releases or gains a lot of energy, that's going to have an impact on our free energy change overall. So this is something that you've probably seen also in a table that looks something like this. So if we look at this, I think that it's helpful to be familiar with this bar graph on the left, as well as this table. So this table, let's compare table 1, 3, and A, D, C, and D. So if we've got part 1 of this, the reaction is both enthalpically favored and entropically favored. It is spontaneous at all temperatures. It is exergonic at all temperatures. What does this one correspond to of these 4 right here? See, which ones of them say exergonic? Is it A? I've got to vote for B. Why do you say B? Oh, yeah, that's the right answer. Well, for starters, it's exergonic. Then the other one that's exergonic, well, as we can see, the magnitude of this bar right here, if we shrank that bar, what do you think is going to happen to this delta G right here? It's going to shrink. It's going to go up as well. Does everyone follow that? So this is a figure that I think is a good one to know about, because all of this information's organized in a slightly tricky way. Because you can look at this and say, okay, well, this is probably A. The first one's probably A. The second one's probably B. That's how it tracks. But no, look back at these. This corresponds to B. Okay. The next situation where we have delta H that is negative and delta S that is negative. well, let's see. The reaction is enthalpically favored, but entropically opposed. It is spontaneous only at temperatures below T delta H over delta S. So this is giving us a ratio of our delta H and our delta S values. So at specific temperatures, we're going to get this sort of reaction take place. So I think what I prefer is this graph on the left-hand side. It's more helpful for me to look at my delta H's and my T delta S's to come up with, well, what is my delta G value? Okay, so then what information can we get? Let's see. Where are we? 26. Okay, cool. Okay. Oh. 26, where I wanted to go. Okay. What direction reaction will go is what we're going to get from delta G. If the forward reaction is favorable, then the reverse reaction is not favorable. If the initial concentration of A is above its equilibrium, the concentration that, or then its equilibrium concentration, then the reaction will proceed towards B. Now, if the initial concentration of B is above its equilibrium concentration, then the reaction will proceed towards A. So direction of the reaction, basically, this is a good way to think about it in terms of, well, if our equilibrium concentrations of A and B are set, then delta G is going to be 0. What is our concentration of A at equilibrium versus what it is actually? Are we going to be going towards B? Then that's what we should expect. Okay, how much useful energy can be derived from this equation? H represents the total energy, S represents the wasted energy, and therefore G represents the useful energy. Delta H, your total energy, is equal to your useful energy plus T delta S. This is rearranged, so that's why it is plus T delta S as opposed to minus T delta S. So it's delta H is equal to, delta G is equal to delta H minus T delta S. If the initial concentration of A is above its equilibrium concentration, then the reaction will proceed towards B. The amount of useful energy derived from the reaction is dependent on how far the initial concentration of A is above its equilibrium concentration. The free energy change, or delta G, of any reaction is related to the ratio of equilibrium and non-equilibrium, which is also known as your Q value. So ultimately, what we can do is we can figure out our delta G related to our initial concentration. So this delta G is equal to minus RT ln KEQ plus RT ln your initial concentrations, which effectively you could also look at that as your Q value under non-equilibrium conditions. Now, free energy change, delta G, is a measure of how far a reaction is from equilibrium. Okay, wrong button. And so with that, where I really wanted to get to today, I'm gonna breeze through this just to come back to it on tomorrow's day. What I wanted to bring up was this idea of energy coupling. So when we have reactions that are unfavorable, and we can combine them to one another. So one example of this is the phosphorylation of glucose. And this is where we're getting into sugars. Glucose is a 6-carbon molecule. It's a polyhydroxyl aldehyde, or aldose. It is a sugar, and glucose gets phosphorylated to make a molecule known as glucose 6-phosphate. If you're familiar at all with the metabolic pathway known as glycolysis, that is the first reaction in glycolysis. This reaction with a delta G naught of 14 kilojoules per mole. Oh man. Well, the phosphorylation of glucose to make glucose 6-phosphate. One thing that's important to recognize about this is PI, indicating inorganic phosphate. So just a PO4 3- molecule. So adding that random floating around phosphate group onto glucose, is this a favorable or unfavorable reaction? With a positive delta G value. Unfavorable. There's always the risk when you're the first person to answer, especially when it's like a binary question. Favorable? No, I meant unfavorable. You're absolutely right. You did mean unfavorable. So that is an unfavorable reaction. Meanwhile, this reaction right here, ATP. Where's ATP generated? Where do we like to generate it? In the powerhouse of the cell, in the mitochondria. ATP is a very powerful molecule. Does anyone know what ATP stands for? That's right, adenosine triphosphate. There we go. Oh, it sounds like a handful of y'all just waited for me to say the first part and then definitely jumped in with the triphosphate. You're absolutely right. Adenosine triphosphate. ATP gets hydrolyzed, gets broken into ADP and inorganic phosphate. And that's the foundation of like most everything that, this movement right here, my fingers moving. And any sort of muscle movement is based on that hydrolysis. We have a delta G naught of negative 30 kilojoules per mole. Favorable or unfavorable? If we said the first one was unfavorable, what do we think about a negative 30 kilojoules per mole? Favorable. You can even say that this is a more favorable reaction than this is an unfavorable reaction. Everyone agree with that? Okay. Now, with that in mind, if we wanted to look at this almost like a Hess's law sort of reaction, are there any species, like if we line up these two reactions, are there any species that are reactants in one reactant and a product in the other reaction? Yeah, that inorganic phosphate, that PI. So effectively, if we were to line this up like a Hess's law reaction, we could say, boom, boom, done with those. And we combine these two things right here. If we were to rewrite this, would anyone object to me rewriting it as glucose plus ATP yields glucose 6-phosphate and ADP? Sounds good, right? That's exactly what's happening with the first step in glycolysis. ATP and glucose are brought together by a specific enzyme that transfers that phosphate from ATP onto glucose to make glucose 6-phosphate. An energetically favorable reaction because we're able to harness these two things. The phosphorylation of glucose, unfavorable. The hydrolysis of ATP, very favorable. Combine our powers together, what do you get? You get Captain Planet with a very favorable reaction, negative 16 kilojoules per mole. Effectively, this is a free energy diagram that's showing those different steps. So glucose getting phosphorylated, this first group right here, going from low energy to high energy, unfavorable. Reaction number 2, from high energy to low energy, favorable. Combine them, and you get something going from relatively high energy to relatively low energy. Those two things are coming together. Now, with that in mind, let me jump ahead here. When you take a metabolism class, this is the slide that I always like to show first, that I've always been shown first, because it's like, yeah, what's up? This is the Reddit make you feel bad post where it's like, I know this stuff. And the truth is, when you take a metabolism class, you start right here with glucose. And you kind of stay like this right here is glycolysis. Photosynthesis feeds into that. Then we've also got the Krebs cycle and the tricarboxylic acid cycle. And then we've got this process of oxidative phosphorylation. So when you take a metabolism class, you kind of just take a class where you get this figure that's really dramatic. Wow, that's a lot. And you make like a duck. It's a duck bill right there. And that's the heart of what you're learning. Now, for this class, what we're going to do is we're going to look at that. We're going to use different components of that to gain a better understanding of enzymes and how they function. Then we're also going to talk about oxidative phosphorylation and the tricarboxylic acid cycle. We won't talk about photosynthesis. If you go on to take metabolism, you're going to take a much deeper dive into all of these things. So I don't want you to think like, oh, well, I've got everything that I need. I need to take metabolism. Similarly, or sorry, on the other side of that, I want you to think if you're preparing for the MCAT, which I know a handful of y'all are, we have till 350 or 340. Yeah, and everyone knows it. 40, exactly 40. One thing that I want you to know is if you look at the AAMC standards for what you're going to be asked over in the biochemistry section, is there metabolism on there? Absolutely. Now, traditionally, 4375 has been taught. And if you go to UT, if you go to A&M, if you go to UTSA and you take a first semester biochemistry class, you will not get exposure to metabolism. The AAMC standards say, oh yeah, you need to take the MCAT, well, take a biochemistry class. And so it's almost this mixed message of they don't know what they're telling people to take, or they don't realize that what they're telling people they need to take is inadequate for the test that they're going to be administering. So what I want you to be familiar with is some of these things. So if you're taking the MCAT, you'll get a little bit of that exposure. In addition to that, I feel like I said at the beginning of class, like if you are taking Spanish 1 and you learn to conjugate verbs, but you never read a sentence, it's almost like it's trivial knowledge. You're like, aha, I know this word, and I'm not even going to try to butcher any words in other languages because that's all that I did in French when I took it, and that's all that I did in Spanish when I took that. At any rate, this is glycolysis, and what I was just describing with respect to glucose getting phosphorylated is this right here at the beginning. We have glucose at the top, a ringed polyhydroxyl aldehyde or aldose, 6 carbons, and it gets phosphorylated with the help of ATP to make glucose 6-phosphate. Now, there's a handful of enzymes in this that I want you to know about. Hexokinase is one of them. Tomorrow, we'll bring back the stuff that I did not cover today, and we'll go deeper into sugars and their structures and how they are different from one another. You should expect that PowerPoint posted before, I'll say before 8 a.m. tomorrow morning. And I like to say that because it sounds like that I can get up at 7:35 and I gotta finish this one. No, I gotta finish it tonight, but I just don't want to say like 10 p.m. because then someone's gonna email me at 10:01 and be like, "This PowerPoint." And I'll be like, I don't know. Could be somewhere. At any rate, we'll talk about this. Expect some top hat questions over this sort of stuff tomorrow. And like I said about top hat, it's going to be there. You finish it kind of at your own. Treat it almost like a homework or review. Deal? Okay, I'm going to close this. I'm going to stop the recording. And I hope you all have a wonderful day. If you have any questions, feel free. I'll hang around for just a minute. Stop recording.